Greetings and welcome. This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the work, energy and power principles for problem solving using work energy method. The course outcome of this session would be the calculate forces resulting in the movement of the connected bodies by using the work energy equation involving springs. The topic covered would be work, energy and power, principles of problem solving using work energy method. Topic learning outcome would be understand the principles related to work, energy and power for solving the engineering problems. So first let us see the introduction of the work and energy. Generally, the work energy approach is used to solve the kinetic problems merely when velocities are involved rather than the accelerations. Okay, so when the forces are involved and then velocities are given rather than the acceleration terms. Like we know that the force is mass into acceleration. If at all the accelerations are not given and the values of velocities are given, then this work energy principle or work energy approach will be useful for solving the kinetic problems. First, let us understand what work is. Work done by a force on a moving body is defined as the product of force and the distance moved in the direction of the force. So, as this definition indicates that whenever there is a force that is being applied, the object will be moving, right? So, in this case, what happens? We can say that the work is done because of the application of the force in the system. So, we can calculate this quantity. The quantity of the work can be calculated by utilizing the product of force and the distance in the direction of the force. The distance the object moves in the direction of the force. The work done can be obtained using this formula, where whenever the system is involved with some force and the object is moving, so this is a dynamic problem, where the objects are moving and the involvement of forces are happening. And this directly implies that the force is making the object to move. So for calculation of the work done, what we do is we will be selecting the force that is causing the movement of the object and the displacement or the distance in which the object is moving in the direction of the force that is applied. So directly we will only consider the forces and the displacements which are in the direction of the forces. So in this image you can observe here, there is a object that is placed on a surface. And a force P is being acted here. A force P is being acted here onto the left side. That means the direction in which the force is acting is towards the right side. And because this application of the force, let us say this object has moved to this position. The object has moved to this position. So, and that condition or that position is at a distance of S. That position is at a distance of S from the initial condition. So, here we can say that the work done can be treated here as P, that is the force applied into S. And S is the distance to which the object has moved, and that movement is also in the direction of the force. Okay, so the displacement or the distance that we will be considering here would be perfectly in the direction of the force. The distances will be considered in the direction of the force alone. So work done equation can be given as W is equal to PS. For the same situation, let us say the object is being applied with some inclined force P, inclined at an inclination of theta to the horizontal. Okay, and because of this force also, because of this inclined force also, let us say the object has moved here to a distance of S. Then here when we consider the work done, W, what we have discussed till now, we should be considering the force that is being involved, okay, in the direction of the movement, right? Force that is being involved in the direction of the movement. So obviously this object has moved in this straight line. Obviously the object has moved in this straight line. So this inclined force, it is not in the direction of the movement of the object, isn't it? So what we will do, we will resolve this inclined force into mutually perpendicular components, so that this is your vertical component and this is your horizontal component. Now we can say there is a force that is involved in the direction of the movement of the object, and that force is P cos theta. Okay, it is P cos theta. So we can write here as P cos theta is the force that is involved in the movement of the object. In the direction of the object, we need to understand. Into the distance moved by the object, which is S. So this is how we need to consider the work done forces, the forces which are involved in the system that is making the object to move. So always we should consider the work done with the forces that are involved in the direction of the movement of the object. So that would be P cos theta into S. So the value is P cos theta S. Thus, the work done by a force may be defined as product of component of force in the direction of motion and the distance moved by the body. Okay, product of component of force in the direction of motion and the distance moved by the body. This is how we will be considering the work done values. Units of work done. The unit of work done is Newton meter, where the work done is treated as force into displacement. The force term is Newton, the unit of force is Newton, and the distance unit is meter. So the unit of work done is the Newton meter. So this Newton meter is termed as the joule. Okay, this Newton meter is termed as the joule, and joule is defined as the amount of work done by 1 Newton. Right, amount of work done by 1 Newton when particle moves 1 meter in the direction of the force. So that is the definition of the joule. So the definition of the joule states that 1 joule is defined as the amount of work done by 1 Newton when particle moves 1 meter in the direction of the force. And kilojoules, if at all the quantity, the magnitude of the work done is more, then we can measure it using the kilojoules mode. And this kilojoules can be treated as kilonewton meter. And millijoules is treated as mj, that is millijoules, which is given as Newton millimeter. So Newton millimeter units will be considered for the millijoules case. Now let us see the concept of energy. Energy is defined as the capacity to do work. So definition of the energy, the units and concepts, everything will be similar to the work done, but the energy is defined as the capacity to do work. The mechanical energy is classified as potential energy and kinetic energy, right? So whatever energy that is being involved in the system, that mechanical energy, it is being classified into potential energy and kinetic energy. First, let us learn about the potential energy. The capacity to do work due to position of the body is treated as the potential energy. The potential energy can be seen here, the representation, where there is a body. There is a body that is present at a height h from the ground. At a height h from the ground. For this type of situation, what we can consider is because of the position of the body, at certain height, we can say the energy is possessed by this body, and that energy is involved because of the position from the floor, or we can say from the ground, right? And this representation can be achieved by potential energy is equal to W, which is the weight, into height, that is h. Similar case as our work done, right? Work done is equal to force into displacement. Here what is happening? The weight is the force term here, W, and the direction in which the weight is acting or the force is acting, and the distance to which it is moving, that is h. So directly we can say potential energy is equal to W into h. So when we convert this to mg, we can say it as mgh. So P is equal to mgh is the representation for the potential energy. Now coming to the kinetic energy. The capacity to do work due to motion of the body is termed as the kinetic energy, right? So potential energy is due to the position of the body, and the kinetic energy is due to the motion of the body. And the equation, the representation of kinetic energy is given as half W by G V square. And this W by G V square can be treated as half mv square. So this is the kinetic energy of the body, where v is the velocity of the body, and the unit of energy is same as work. So same joules is the units for this energy also. Now let us learn about the power. Power is defined as rate of doing work. Okay, and the unit of power is treated as watt, represented with uppercase letter W, and is defined as joule of work done in 1 second. So the rate of doing work, nothing but work done by second, right? So that will result as joule per second. So that is joule of work done in 1 second. So power is equal to work done by time, and the instantaneous power developed by a force F. You should be careful here. The instantaneous power developed by a force F moving at a speed V. So whenever the object is moving, whenever the object or any body is moving because of the application of the force F, and it is moving at a speed of V, then directly we can consider the power as P is equal to force into velocity V or speed V. So that can be given as P is equal to F into V watts. So power can be calculated using this formula also. The force that is involved in the system and the speed or velocity with which it is moving. P is equal to F into V watts. Then horsepower, it is represented as 1 metric HP is equal to 735.75 watts. Also, 1 British horsepower is equal to 745.8 watts. So this is regarding the work, energy and power. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.